Hello, and welcome to Lecture 13 of AMAT502 at UAlbany. Today, we're going to start the second half of our course, which is where we finally get into the aspects of machine learning that all of you have been so interested in learning about. Our first example of machine learning is going to be regression. But before we get to all of that, I'm going to try to outline what are the basic philosophical understandings of what it means to learn. This, I think, is essential in order for you to have a broader view of what machine learning is. In particular, how do we know how we learn before we can teach a machine to learn as well? So the topics for today are going to start off with some more historical context. In particular, I'm going to contrast briefly two versions of what's called epistemology. Epistemology is the study of how we know things. First, I'll start with Plato and sort of the Greeks, and then I'll move from the west to the east and do a quick survey of some Samkhya philosophy, which is the underpinning for a lot of orthodox Hindu schools of thought. You'll be surprised to see which one actually is more closely connected to machine learning. Once we get into machine learning, I'm going to outline what are the really two main principles of machine learning. And here I'm going to rely heavily on our book by John Guttag, where we emphasize the train model predict paradigm. And then we move on to view learning as an optimization problem. Finally, we specialize in the case of regression, which is something that some of you are familiar from using just basic statistics. And we'll get into some of the issues that appear there. So I want to encourage you all to have a philosophical view of learning. And to quote the famous Dr. Seuss, it is better to know how to learn than to know. So I want you to ask yourself the question, what does it mean to learn something? If it's better to know how to learn, then we should know how we do learn. Your answer to this question reveals something about your epistemology, which is the philosophical study of how we acquire knowledge. These are questions that have intrigued thinkers around the world for thousands of years. Our first stop on this tour is going to be that of Plato. In case you don't know, Plato was a famous Greek philosopher who lived from roughly 430 BCE to about 340 BCE. He was a student of the famous Socrates, and Plato was also a teacher of Aristotle, who laid so much of the infrastructure for knowledge as it was formed and principal object of study for the scholastics through the medieval times, and then continued to affect things up until the scientific revolution. At least that's a very Western view of things. So one of the things you need to know about Plato is that he described his philosophy not in lengthy essays, but rather in dialogues where prominent ancient Greeks of the time would just gather to talk. Back then, we didn't have as much to do, and Greeks having an agrarian society, which was not operated by the elites had plenty of time on their hands to take up issues of the mind. So often in Plato's dialogues, he's going to show several Greeks talking, and Socrates is going to be his mouthpiece for arguing about whatever topic is under discussion. So you should have this kind of picture in your head of a bunch of aristocratic Greeks gathering and lounging about to discuss deep philosophical concepts. So the reason I bring this up is because Plato outlines one of the most famous paradoxes of learning. This is called Meno's paradox. So this is considered one of his most famous dialogues. And in this dialogue, Socrates and Meno engage in a discussion of virtue. Of course, for the Greeks, one of the hardest philosophical problems was how do we come up with a rational basis for ethics? And so Meno goes to that, but it quickly moves across several very deep topics. It starts with first an unsuccessful search for the definition of virtue. How do we recognize virtue or whether someone's being virtuous? And this leads into Meno's paradox, which is how do we actually learn things? And then Socrates counters with the proof that knowledge is innate. And then this leads into further discussions of like, if a knowledge is innate, can we actually teach virtue, or is it just something we all need to know sort of internally? And this also concludes the discussion why there are no teachers of virtue. So Socrates' proof that some knowledge is innate is in response to a sort of clever rhetorical trick by Meno. And he says the following: either we know something we don't, and if we know it, he says, sorry, we either know something or we don't know. Obviously, if we know it, then we don't need to inquire any further. So we're done. But if we don't know something, how can we inquire it? Because we don't actually know what we don't know. And so in particular, if we don't know it, how do we know when we found it? So this sort of sounds like a clever trick, but it illustrates an issue of like, how do you acquire new knowledge? And so Socrates has a very interesting response to this. And in fact, it reveals some of the more mystical aspects of this supposedly rational Greek philosophical universe. And indeed, what he does is he relies on the testimony of priests and priestesses who claim that the soul is immortal. And he relays one of these myths of Persephone before saying this long quote, but I'll read it to you. It says, "The soul, then as being immortal, and having been born again many times," so this notion of rebirth, "and having seen all things that exist, whether in this world or in the world below, has knowledge of them all. And it is no wonder that she should be able to call to remembrance all that she ever knew about virtue, and about everything. For as all nature is akin, and the soul has learned all things, there is no difficulty in her eliciting, or as men say, learning, out of a single recollection, all the rest. If a man is strenuous and does not faint, for all inquiry and all learning is but recollection." So the two key parts of that are that the soul has learned all things. And this comes from this sort of cycle of birth and rebirth, and the ability for the soul to voyage outside the body and travel into other realms. But the key line here that I want you to remember is that for all inquiry and all learning is but recollection. So this is a pretty mystical idea. And in fact, what Socrates is doing here is he's channeling something from Pythagoras, who you might associate with the Pythagorean theorem, but he was also the leader of a pretty interesting cult and had a weird fear of beans, refused to eat beans. So this idea that all learning is recollection is an illustration of one of Plato's epistemological principles. Again, epistemology is the study of how do we know things. And this principle is called anamnesis. So anamnesis takes a very radical viewpoint, which is that learning is in fact impossible, and that in fact all learning is an act of remembering. So Socrates proves this, and I'll use scare quotes there, by talking with Meno and then involving one of the slave boys who happens to be around during this dialogue. And so he's a young kid, has no education, and certainly has no education about Euclidean geometry. And Socrates asks the slave a very interesting question, one which I hope you can answer. And the question is this: suppose I have a square that is 2 feet on each side. So it's a square, so the side, height and width are the same. They're 2 feet on each side. And he tells us, okay, so the area is 4 square feet. How long must the sides of a square be whose area is twice as much, namely 8 square feet? Okay, so this is a convoluted way of asking a question, but what he's essentially asking for is, what is the square root of 8? In particular, how do we find a square's side lengths whose area is double the area of another square? As you know, this gets quickly into some issues of the square root of 2, which is one of the things we considered at the start of our course. So Socrates has asked the slave boy, all right, tell me how can we find the side lengths of a square whose area is twice as much as a square whose area is 4 square feet. And so the way this goes is sort of a trial and error. First, the boy guesses that doubling the length of each side will produce a square twice the area. And then Socrates asks, well, okay, if you think that's true, go ahead and take the square I already gave you, and now double each side. And then tell me, what do you think the area is? And so the boy observes that doubling the sides is too much. And in fact, doubling the side lengths leads to 4 times the amount of area. You can put the same square in 4 times. So he proceeds in this sort of trial and error method. And he says, well, if I start with something that's 2 feet per side, maybe I should try 3 feet per side. And then again, he sees that this ends up being too much. Of course, we know the answer is 9 square feet there. And so Socrates then draws a figure, and he does this. He makes the observation that if I give you this square, which has 2 feet on each side, then the way to double the square's area is to create a new square whose edge length is the diagonal of the previous square. And that you can just see by counting, well, this has half the area, but now we have 4 halves of the area of the original square. And we've thus accomplished our task of doubling. And notice he was able to do this without ever appealing to or wondering about the irrational nature of the square root of 2, just simply by constructing and drawing straight lines. So the story that goes there is that by essentially guiding this slave boy through a series of questions and answers, the slave boy is able to discover some fact about Euclidean geometry, which is that by using the diagonal, one can actually construct a square that's twice the area. And if you read carefully the dialogue of Meno, we sort of get the Socrates claims like, look, the slave boy knew nothing about geometry, but just by sort of putting him in the right direction, he was able to remember something about sort of very abstract area of math. And so this idea that, the slave boy is just waking up and remembering this fact is what leads Socrates to conclude that a priori, which means before experience, knowledge is truly possible. And then in its most extreme viewpoint, that's the only way that we actually acquire knowledge. So this works well for mathematics, but not so well for everything. So let's take another stop on our journey around the world. And let's look at some other philosophical systems for how learning is possible. Because after all, if learning is impossible, then why are you taking a course on machine learning? This next stop is going to be over in the Indian subcontinent. And this goes under the broader heading of Hindu philosophy. And so one of the things that gets picked up in Hindu philosophy is a discussion of what are the different pramanas that are possible. These are proofs of knowledge. How do you justify knowledge? And of course, many of you have maybe a picture of Hindu philosophy involving stretching and bending and engaging in yoga, but if you ever read any of the foundational texts of yoga, like the Yoga Sutras, you'll actually learn that the underlying basis for a lot of that philosophy goes to something that's called Samkhya. So Samkhya philosophy is sort of metaphysics that undergirds a lot of the philosophical concepts behind yoga. And Samkhya actually just means numbering or number and enumeration. And it's one of the 6 orthodox schools of ancient Hindu thought. But either way, what differentiates Samkhya from other schools is it accepts 3 methods of proof. So these are 3 methods of acquiring knowledge. The first method is perception, pratyaksha. And the idea here is that sense data is taken in through the eyes, nose, ears, tongue, skin, and turned into an internal representation via the mind, manas, which is in turn interrogated via the intellect, called buddhi, and contextualized via the ego, ahamkara. But these are just examples. There are also examples of internal perception. So Samkhya believes that perception is the way in which we take in knowledge. And this is how we can prove that things are true. We just see and we have sense data. But there are also examples of internal perception, like mathematics. So when you are working on a math problem and you suddenly have an aha moment, that's an example of an internal perception, which occurred without having to use the eyes or nose or ears or mouth. In addition to perception, Samkhya accepts inference as a valid method for acquiring knowledge. The classic example of this is when we see smoke, we infer that fire is present. And moreover, that if every crow we see is black, then perhaps we can infer the statement that all crows are black. So this goes into induction, and something that was struggled by David Hume much later in European and British philosophy. Finally, the third method of proof that's accepted in Samkhya is something called reliable testimony, or agama, or shabda. So if a trustworthy person or scientist reports something, then Samkhya says we can take it to be true. So this concept is also used to justify how we can know something that is reported via an important secular or religious text, such as the Vedas, which was one of the earlier sort of philosophical and religious systems for India. Or instead of the Vedas, we could have the Torah or the New Testament, things which are more familiar to those who follow Abrahamic religions. And I think this is probably a really important one to consider, because actually most knowledge today, if you think about it, is taken on faith. And it's not just blind faith, but someone tells you something and you take it to be true based on the reliability of the person telling it to you. So you think about how do we know that the sun is the center of the solar system? Have you ever gotten on a spaceship and checked for yourself? Probably not. So this is an example of something that we accept based on reliable testimony. Although there are people who carefully study the motions of the planets, and this is what led Galileo to really champion, and Kepler to champion, this heliocentric model of the universe, or of the solar system. All right, so that's some historical context. And to review, we've got Plato, which provides this sort of mystical idea that, no, actually we don't learn anything by observation, that in fact, it's our soul traveling through various realms. And then we remember that as our soul becomes entrapped in our body, and then someone sort of triggers the right sort of memory that then allows you to know that something's true. Or we've got this orthodox Hindu school of thought called Samkhya, which tells us that we can go by perception, we can go by inference, or by reliable testimony. And those are sort of acceptable ways of acquiring new knowledge. So let's look at a slightly more modern perspective, which is maybe communicated with not a lot of fanfare in our book, Introduction to Computation and Programming Using Python by John Guttag. So he says in there, in a way which betrays his epistemology, and he asserts that humans learn in two ways: memorization and generalization. Humans use generalization to deduce new facts from old facts. So I want you to take a moment to think carefully about which method of proof or proofs that I just outlined in Samkhya is Guttag implicitly using here. So take a minute to think about that. So maybe we should go back and look briefly. So we've got perception, inference, and reliable testimony. Well, generalization is really perhaps another way of just saying inference. You know, we start with some observed data and then we generalize from that. So he's actually using this method of inference, which is also called anumana in Sanskrit. And then memorization is actually an example of perception. In order to actually remember something, you might need to first perceive it, and then hopefully it's stored in memory. But there's also, memorization here is also possibly a code word for reliable testimony. Someone just told you, you looked it up in a book and you remembered. So all three methods of proof are actually being sort of relied upon in Guttag's definition. So let's look at why this definition is suitable for machine learning. So Guttag's definition of learning, memorization and generalization, the reason he uses that is it's conveniently applied to computers. And so, in fact, he says, when computer scientists speak about machine learning, they most often mean the discipline of writing programs that automatically learn to make useful inferences from implicit patterns in data. So that's a data-focused definition. But it also gives meaning to the term learn in Arthur Samuel's definition of machine learning, but Guttag also cites. It says that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So Arthur Samuel was a computer scientist in the 50s and 70s. He was one of the first to program a computer to play checkers. And this program would improve based on experience. So again, our notion of memorization or also perception, all these go into what constitutes experience. So at this point in our class, we now have a definition of machine learning. Ideally, we want our machines to be able to learn without being explicitly programmed. And so learning here actually means making inferences based on some training or implicit data. So let's go through that in a more succinct way. And so this is perhaps one of the most important concepts for the second half of the course that I want you to really understand. So this is the idea that learning really fits into a paradigm, which I will call the train, model, predict paradigm. So in step one, we first observe a set of examples, which is called training data in the field of statistical machine learning. We then use inference techniques to create a model of the process that generated the data. And then finally, we use that model to make predictions about previously unseen examples. So we first train, and given that data, we select a model. We believe this is the model that generated the data that we trained on. And then once we have adopted a model, we can try to make predictions so that we can predict what new data or what new instances might produce. So learning in statistical machine learning is about training, it's about modeling, and it's about predicting. So let's see how we can do that. So let's start with an even basic example that probably many of you have encountered taking some standardized test. And let's just ask how we as humans would apply the train, model, predict paradigm to a very classical subject, namely number sequences. All right, so the first sequence we have 2, 4, 6, 8, and 10. So 2, 4, 6, 8, and 10. What number comes next? Well, if we look at it, we see that in our training data, which is this first 5 sequences of numbers, the difference between each number in the sequence is 2. So I add 2 to 2 to get 4, and I add 2 to 4 to get 6, and I add 2 to 6 to get 8, and I add 2 to 8 to get 10. So my model is that the sequence of numbers is generated using a difference of 2 pattern, or schema. This allows me to predict that 12 is the next number in my sequence. And indeed, it should be. So let's try this again on the next sequence. All right, it's 3, 8, 13, 18, and 23. So that's our training data. Well, just based on the example we already did, one useful trick might be, let's see if the differences between each number is the same. Ah, yes, it is. So I go from 3 to 8 by adding 5, and I can go from 8 to 13 by adding 5, and I can go from 13 to 18 by adding 5, and so on. So this leads me to predict that the next number in the sequence should be 28. Okay, so far so good. What about this next sequence? So I have 2, 5, 10, 17, 26, 37. So I already see that these sequence of numbers are growing much more rapidly than the previous sequence. I'm also given more data. I have now 6 samples. So what's the pattern here? Is the difference between each number constant? Well, the difference between 2 and 5 is 3, but the difference between 5 and 10 is 5. The difference between 10 and 17 is 7. So 3, 5, 7. 9. So 3, 5, 7, 9, 11. What would you predict the next number is? I'll let you think about that. But one thing we know is that the model which is used to describe this sequence of numbers is not the same as the model over here, because in these last 2 examples, the difference between each number was constant. And here we see the difference is changing. How is it changing? I'll leave you to think about that. We've got one more example. So 1, 5, 6, 11, 17, 28. So the difference between each number is 4, and then 1, and then 5, and then 6, and then 11. This is an instance of a Fibonacci type pattern where the difference is proportional to the number before. So I just add the previous number to get the next one. Or I add the previous 2 to get the next one, because 6 and 11 is also 17, and 11 and 17 add together to give 28. So is there a general pattern for the difference? Yes, it's sort of recursive. It's based on what was before. So we have a model of constant difference, a model of a growing difference, and then a model of a self-similar distance. These are all 3 different models which enable us to predict, in which we formed this model based on observation, perception. So hopefully by now you've figured out that third example. And again, if you're going through this pretty quickly or you're late, it's late and you're maybe tired, it's okay if you didn't get them all. But one thing you always want to know whenever taking any class is, how good are you doing? How far off are you from understanding things perfectly? We can use the term, we want to assess the quality of our model. So Guttag argues that there are 3 universal features of learning, which all pertain to model selection. So inside of our train, model, and predict paradigm, we're going to further break apart our modeling step into the following 3 components. So first of all, we need to have a notion of representation of our model. The second is we need a penalty function, which is sometimes called an objective function, that allows you to assess how good or badly you're doing. And then finally, we need a method which allows us to go from worse performance to better performance, or one which allows us to minimize the penalty function. So in this first case of representing the model, here we had a number sequence, and we were trying to predict the next one. And we selected various ways of determining that increase in sequence. So one could just be, oh, we're adding the same constant number. Now, suppose I revealed to you what the next number in the sequence was. Well, you could use the absolute value of the difference to provide a penalty function. And then you need to figure out a way of how do you change your model in order to help minimize this penalty function. So, and the difference between the first two examples and the third, if we assumed a constant difference, we would have been wrong. And so one way in which we might want to change our model is to change how quickly we allow each term to grow. Well, I'll give rigorous mathematical meaning to that shortly. So let's spell out in closer detail, what does it mean to understand our model and how to represent our model here. So one broad class of models for understanding sequences is that there is a function that relates inputs with outputs in a deterministic way. Remember, determinism is different from stochastic, meaning that it's impossible to predict. So a function is deterministic, generally speaking, which means that whenever I have some inputs, I get an associated set of outputs, and the outputs never change if I give it the same input. So we can treat this pair of numbers as training data. And a coarse model is that these values are related by a function. And so we just use yi is equal to f of xi. That's what we mean when we say that yi is the result of applying the function f to the input. So model selection then, once we assume there's a functional relationship between our values, is how do we actually choose the function f? And so this is the thing that allows us to predict our yn from our xn, or that's going to be, say, our nth value from our nth step in the sequence. So I just want to bring up a warning. So technically speaking, most real-world data is never related by a true function like this. Because in mathematics, a function is defined as something that associates to each input a unique output. But we all know that that's not true. So for example, weight is not exactly a function of height, because there can be people who have the same weight, same height, but different weights. So this is an example of how there's stochasticity involved. And so there's some sort of variation, but we can still get trends which are functional. So how do we get these trends? So the classic method for learning when we have these sort of number sequences and associated values is called regression. So given a collection of x values and y values, we're going to assume that one variable is independent. This is usually the x variable, and another variable y, which is dependent on x. So that means that y depends via the function f on x. And so a very nice model for modeling these kinds of dependency relations is to assume that f is a polynomial. What that means is that I can compute my values y using some linear combination of weights of x and possibly x raised to some power, such as x squared. These coefficients, these beta, are sometimes called the unknown parameters in our model. And these are things that we need to estimate from our data. So in the process of training, we're observing our data. And once we've selected this model, namely this polynomial relationship that relates x values with y values, we can then try to train to optimize our coefficients, beta, these are unknown parameters, so that we can try to predict what future values of y are as a function of x. So notationally, sometimes you'll see f of x comma beta, or even just f of x given beta, like in the language of conditional probability. Linear regression is a special case of regression where we assume that there's no higher order dependencies. So meaning x squared and x cubed, et cetera, there's no influence there. So beta k is equal to 0 for those values of k. So we now have a way of selecting our model, and then we might even be able to choose some initial guesses for what these unknown parameters would be based on data. But we want to be able to assess how good our predictions are so that we can then modify our choices of beta. So this is done via what's called the sum of squared residuals. So residuals are just sort of how far off are you? So the sum of square residuals associated to f of x beta, or again, f of x beta is just that polynomial in x where the coefficients are beta 0, beta 1, beta 2, and so on. So that's our definition of f. And so if we want to assess our penalty function, which determines how far off we are, instead of just looking at the absolute value of the difference, what we're going to do is sum over all of our observations. That's all of our xi, it's our training data. We take our sort of candidate model for the functional relationship between x and y, that's called f. We evaluate f on all of our training x, and then we just sum up the squared difference between yi and f of xi. And so this idea of learning as being one which minimizes penalty is achieved using a method called least squares. This was actually something that dates back to Gauss in the 1800s. And so there, Gauss said, let's declare the best model, f of x beta star, so it has a stellar performance, is one that satisfies that f of x beta minimizes the sum of square residuals across all possible values of beta. So here's a quick question. Why would we use this sum of squares and say not the absolute values of the differences, for example? Lots of ways we can measure the difference between things. And why do we use a square instead of a cube, for example? I'll give you some time to think about that. So I'll go and say one possible answer is that if we were to use, let's say, absolute values instead of squares, that's going to be a hard quantity to deal with, especially back in the days of Gauss, where everything had to be computed by hand. Because in fact, as we're going to see now, the way we compute our best model is by using differentiation, and differentiating absolute values is quite complicated. So this leads us to how do we solve this optimization problem? So again, learning here is choosing this best value beta star and saying that this is the model which models my data. One of the nice things about linear regression, and where I use this method of least squares, is that we can actually come up with exact formulas for beta 0 and beta 1. Again, in linear regression, we only need these two parameters, beta 0 and beta 1, because we're assuming that beta 2 and beta 3 and all the higher ones are 0. So if you write down, okay, S is this sum of squares across all my observations, then this gives me a function defined on R2, where one coordinate corresponds to beta 0 and the other coordinate corresponds to beta 1. So we have those two dimensions of parameters that we can vary across. And so just like when we use in one variable calculus, we try to find what is the local maximum or global maximum or global minimum of a function. One way we can approach that is by taking the derivative and setting it to 0. The same exact same thing is true for two dimensions. So when I have multivariable calculus. So here is what I do. I take S and I take the partial derivative with respect to beta 0, and I set that to equal 0. And I also take the derivative of S with respect to beta 1, evaluate it at my sort of candidate point, and set that to 0. And so with these two equations, I can determine the two unknowns, beta 0 and beta 1 star. So I've linked to a reference which actually goes to the derivation. It can be a little complicated, but you end up finding that one way of computing beta 0 star is we take the mean of all the x values, that gives us x bar, and then we take the mean of all the y values, and then we just look at y bar minus beta 1 star times x bar. And that's our value for beta 0. But that doesn't tell us what beta 1 is. Beta 1 star still has to be computed. And in fact, the way this is done is we take what looks like the covariance of my values of xi and yi about the mean. So I essentially take this product of how much does xi vary across the mean times how much does yi vary across the mean of all the y values, sum those up, and then I just divide by the sum of square difference. This is actually the variance of the xi's. So beta 1 star is actually expressible in terms of a square root of the covariance across x and y and the variance of x. So let's go ahead and implement this and plot it and try looking see how this looks on various things. So you'll see here that I define a function called estimate coefficient. And here I use my NumPy methods of the mean of x and the mean of y. And now I compute these sort of cross deviations, which is just sort of the deviation across y and x for each of these values. We call that SS sub xy and SS sub xx. So those are my top and bottom. And I just go ahead and write in Python the formulas I just showed you. So B1 is equal to SSXY divided by SSXX. And B0 is the mean of y minus B1 times the mean of x. And then I can just return that as a tuple, beta 0, beta 1. So that's what it means to estimate my coefficients. And so then, if I want to predict, I do this using my plot function here. But the key point here is the way I predict values is that if I'm given a candidate value of x and I want to know what does my model predict y is going to be, well, first of all, I go ahead and use my tuple of values returned from estimate coefficients, look at the 0th entry, and then I look at the first entry. And this just gives me the equation for the line. And then I evaluate that on x, and that gives me my value that's predicted associated to y. And so now I can plot my values of x along with their predictions. I'll use a green line. But then I'll also go ahead and show how this compares with y, wherever that is my chosen set of values. So let's look at this example that I showed earlier, where I had an 8-term sequence where it appeared to be growing according to something that was non-constant. So meaning I went from 2 to 5 in step 3, went from 5 to 10 in step of 5, and then a step of 7, then a step of 9, and then a step of 11, and then a step of 13. So you can hopefully now see that the third model was governed by taking increasing odd numbers and letting that be the difference between each consecutive term. But if I assumed that there was a linear model, so I'm going to do linear regression here, we're going to see that this probably doesn't work, but let's go ahead and see what happens. All right. So that stores all my functions in memory. Let's go ahead and plot. So you can see here, here's our training data, and here's our model, which is that this is uses a single line. And for this example, we see that we're actually below the model down here, or above the model down here, and below the model over here, but then going up again. That's essentially because, as you might realize, there's a quadratic relationship between x and y. Now, if I had chosen a slightly different set of values, then I would have gotten one that actually has a linear fit. And indeed, I go back here and I go ahead and change this value, say y equals np.array. Maybe let's use the one that always went up by 3 each time. So I'll just go ahead and say 3, 6, 9, 12, 15, oops, 15, 18. One these to match lengths. So I've so far gotten 6 entries, 21, 24. Right, that should be 8 entries. So I could toggle back and forth between these. Now let's go ahead and plot. So here I got a perfect fit. And that's just because in this case, there actually was a linear relationship. But I'm going to go ahead and turn this back to what it was. So this plot exhibits a phenomenon in regression known as underfitting, meaning it doesn't fit the data particularly well. And in particular, we see that in this case, a linear function is not the best fit. So this is something that we can correct by changing our model. And so here, we'll still assume that there's a polynomial relationship, but we're going to up our degrees from just going from a 1 degree, first degree polynomial, means something that's linear, to a second degree polynomial. So to do this, I'm going to go ahead and bring in some of tools from Pandas, which I import as PD. And so here, I'm going to go ahead and bring in a comma separated value sheet, which has my data, and I'm going to run my sklearn model, specifically linear regression. But this actually allows me to play around with fitting using higher degrees or polynomial regression. So the way I do that is I have from my pre-processing, I'm going to assume it's a polynomial of a higher degree, and I specify this polynomial's degree by saying poly equals, so this creates an object that's an instance of this class, polynomial features, whose attribute is degree 2. And so using my data, x, I'm going to transform or modify the coefficients of this polynomial according to the values in x. So again, x here, I'm saying is actually equal to this comma separated value sheet. So let's go ahead and run through some of this. And so once I've done that, I now can actually fit my polynomial. Well, here, this is the one where I've already looked at some of these newly generated polynomials, and I look at how that polynomial responds and is compared with the values y. And then I could apply what's actually this linear regression method here. And at the end of the day, I end up predicting or plotting my lin2.predict, which comes from a linear regression on this transformation. And we'll get into why that is soon. And this allows me to see that there is actually this functional relationship that is very quadratic. So let's unpack some of what just happened here. So I have my data set stored as a .csv file. And so when I go ahead and return that, so again, data set was equal to pandas pd.read.csv. It goes ahead and does this really nice thing where it shows me as a table. And it says, oh, here are my x values, here are my y values, and these are my number of observations. Now, what happens when I do this prediction step in my train model predict using pandas, where I've done this transform, And I want to ask, well, what's the next number in the sequence? So if you're paying attention, I had, all right, 7, 8. I can see what happens when I plug in x equals 15. Tells me it's 226. Now, let's compare that with the timeline where we just used the linear model. We got 15, predicted value would have been 130. So what this is saying is that here, if I use the linear model instead of my quadratic model, my predicted value associated to 15 is 130. Whereas over here, when I allows myself to use a quadratic polynomial, the predicted value associated to 15 was 226. Obviously, these are radically different. And just given the fact that our number does look like it's a squared plus 1, and indeed 15 squared is 225, so if I add 1, that's 226, then I can have actually extracted my correct model. So all this shows is that we can do some basic linear and even higher regression using polynomials to try to fit some of these number sequences that we just discussed. I encourage you to try that with the sort of Fibonacci looking sequence and see what happens. But there should be a word of caution, which is how do we know what degree polynomial to use if we don't have a really clear fit like the one we just had? And so there's another problem that can happen, which is that suppose my training data consists of this collection of points, right? I have x values and y values, where no two x values are the same. So I predict that there could be a function, or my model is that there could be a function that actually relates x and y. Then there's a fact that there always exists a polynomial that passes through all of those points. And indeed, this is sometimes called the Lagrange polynomials associated to a sequence of points. So if I have n plus 1 points, then I can use a degree n polynomial. So that means if I had 2 points, I can always fit a line through it. That's a degree 1 polynomial. If I have 3 points, I can always fit a quadratic to that. And this is modeled using what's called these Lagrange polynomials, which essentially just take all these values and then selectively divides by one of these values. And then by just putting yi as the coefficient, all the other terms will be 0, and then it'll pick out that value yi when you evaluate on xi. So this will give us a polynomial that passes through all the points. But there's a good reason to believe, just using Occam's razor, that we don't always want to use a model that's as complex as the number of data points, especially when we start looking at 500 and 1,000 data points. We don't want to use a degree 500 or degree 1,000 polynomial to fit everything. So that's it for today. I look forward to seeing you in class soon.